Let's talk about magnetic hard drives. The hard disk drive implies a magnetic disk. HDD or hard disk drive, when we hear these terms, we're talking about magnetic disks. And standard magnetic hard disks are 3.5 inches wide. They go in a standard bay in your desktop computer. And they use multiple platters to store data. So here's an example of a hard drive. This is an illustration of a hard drive with the top taken off. And here we have the platters. They rotate around a spindle, which keeps them in place. And we have read-write heads for each of the platters on the end of an actuator arm, which moves across the platter to read the information from the appropriate sector and track. So we have some moving parts here, and the moving parts can fail over time. So that's one of the reasons for the move to solid state drives. And over here we have our power and data connectors and optional jumper block, which we'll show on a real hard drive in just a little bit. So that's some of the parts there of the hard drive, the internal workings of the hard drive. Are you ever going to fix these? No. Does the A+ exam expect you to fix these? No. But it's good to know how the hard drive works so you have an idea of what could possibly fail. The read-write head might fail, or the arm might fail, and you might hear some noise in the hard drive, excessive noise, which means that the hard drive's about to go. So you want to watch for that. These drives are usually SATA, so serial ATA, and they make use of a 15-pin power connector. And the 15-pin power connector has a vertical tab on the right usually, and it makes it easier for orientation when you're connecting that power cable. And the power supply sends 3.3 volts, 5 volts, and 12 volts to that SATA drive, and those are the orange and red and yellow wires respectively. And you also have your data cable here. The data cable is a 7-pin connector, and that connects here. And let's go ahead and show that on a real drive right now. Here we have a Western Digital 500 gigabyte drive. It's standing on its end. And here are the connectors that we spoke of. This is the SATA power connector, and that port has 15 pins. You can even count them here. And here is the 7-pin data connector. Again, you can actually count these pins so you know which are which. That power connector, as we mentioned, has a little tab here on the right, and that helps you to orient the power connector. The data connector has a little tab on the left. So that's just for orientation. And here we have the jumper block, and that's really only used if you're going to use this drive in conjunction with older IDE drives, which I don't really recommend, and some other special circumstances, but you're rarely going to use that or see it on today's SATA drives. Here we have a circuit board, and that contains the controller chip and the cache memory for the hard drive, and it has a flex circuit which connects to the spindle here, which the platters rotate around, so we can have this communication for the hard drive. So remember, there's moving parts in here, and we have a lot of things going on that SSDs or solid state drives pretty much alleviate any of these problems that you'll have in a hard disk drive such as this. So remember that magnetic hard disk drives, they're still out there. You'll still find them, but they're quickly being overshadowed and overtaken by the solid state drive. Let's talk a little bit about hard disk specifications. There's a couple you need to know, several really. And the first is capacity. The capacity is the amount of data that the hard drive can hold. And so, for example, you might have a 500 gigabyte drive, or you might have a 1 terabyte drive. And the capacity is important. You want to know, how much data are you going to be storing? You want to understand how much data your drive can hold. And, keep in mind you may need a bigger drive later on, or an array of drives, or a good backup system or something. So keep in mind the capacity. Also, when you're dealing with hard drives, when you look at the manufacturer's website, say Western Digital or Seagate, you'll see the drive marketed as say 500 gigabytes. But when you look at that drive in, say, Windows 7, you'll see it as 465 gigabytes. And you're not losing any data, you're not losing any capacity. The reason for that is because the hard drive manufacturer uses the base 10 system and Windows uses the base 2 system, where a kilobyte is 1,024 bytes instead of 1,000. And a megabyte is 1,024 kilobytes, and so on. And so in total, a 500 gigabyte drive will be read by, say, Windows 7 as 465 gigabytes. So that's capacity. Next is cache. Cache is a buffer of memory, and the cache on most hard drives is onboard DRAM. It's right on the circuit board of the drive. And you can compare this with CPUs. CPUs have cache memory, which we've spoken of, and they use SRAM. And that's significantly faster than DRAM. But like the CPUs, the hard drive's cache helps to access frequently used information faster than if it were to get it from the magnetic disk. In fact, a lot faster. You know, your onboard DRAM is going to be much faster than the magnetic disk. So there's capacity and cache. Let's look at our hard drive again and show those on the label of the drive and show what they mean. Okay, here we're looking at the top of the drive and we're looking at the label. We see this is a Western Digital 500 gigabyte Caviar Blue drive, just a basic drive for holding basic data. But we also see here that it says SATA, so we know the type of drive, and it says 16 megabytes of cache, so we know how much cache memory this drive has. Newer drives today have a lot more cache and faster cache. We also see here the model number, WD5000AAKS. Now, it's important to know the cache and the model number, and perhaps even the serial number here, whenever you're replacing a drive, because you should replace the drive with the same drive usually, unless you're upgrading. But also if you're going to create an array of drives, say a RAID 1 or a RAID 5 array, or any type of array, you want to use the same type of drive for all the drives in the array. And you really want to go by this model number when you do that. So make sure that all the drives are WD5000AAKS, because the model names can be slightly different, like AAVS or WD5000ABKS or what have you. So you want to be real careful with that and check that. Make sure that you're using the correct drive, using the same drives for all of them and within the array. We also have a schematic of the connections showing you where to connect the power and the data and so on. And if you have to make any changes to the jumper settings, it gives you that information there. So always look at the label of the drive. It can give you a lot of information that you need to know as far as connecting it or compatibility or exactly what type of drive it is, if you can't find this information within your BIOS or within your analysis software. Okay, getting back to hard disk specifications, let's talk about data transfer rate. The data transfer rate of a hard drive is the maximum amount of bytes that can be sent or received, but it's a theoretical maximum, and the theoretical numbers are never really actually achieved. Generally, you'll get a data throughput amount that you actually are using, but you should know the data transfer rate maximums for SATA, and you can see those are listed here. First, we have SATA revision 1.0, and we see that it's measured in bits and bytes. So 1.5 gigabits per second will basically come down to being 150 megabytes of data being written to the drive per second. Now, you may say, well, why didn't we just divide by 8? And the reason that it's only a tenth of the data sent serially is because of encoding. You have some additional encoding data that has to be removed after it gets to the drive before that data can be written to the drive. So you lose a little bit there. So 1.5 gigabit serial connections will actually store 150 megabytes of data per second on the drive. Then we have SATA revision 2, and you'll see a lot of these drives out there. They're 3 gigabits per second, and they can write a maximum of 300 megabytes per second to the drive. Now, our drive is an SATA revision 2.0 drive, So it has this theoretical maximum of 300 megabytes per second. But this particular drive can only sustain in the neighborhood of, say, 120, 130 megabytes per second. And this is also referred to as data throughput, the actual amount of data that you can send back and forth in your computer, in your environment. So in my environment, in my lab, that's about what I get on this magnetic disk, 120 megabytes per second. The theoretical maximum is 300 megabytes per second. So some food for thought there. Next, we have SATA revision 3, and we have one of those drives going into our AV editor also, and that's 6 gigabits per second or 600 megabytes per second. And now we have SATA revision 3.2. As of the recording of this video, that's the latest one, and that goes at 16 gigabits per second and has less encoding data, so we actually get a better ratio, and it's upwards of 1969 megabytes per second or 2 gigabytes of data per second. So that's a big jump. And that is data transfer rate. A couple other things you should know for hard disk specifications. The first is rotational speed. This only deals with magnetic hard drives. And some examples are 5400, 7200, or 10,000 RPMs or rotations per minute. The rotational speed is something that you might look at when you're interested in how fast the data can be accessed. If you need really fast data access, you want a higher speed. If you don't really care that much, if you just have a computer that's connecting to the internet, you might want to just go with 5400 RPM. Why? Because there's a cost factor involved. The drives with the higher RPMs are going to cost more money. But again, the drives with the higher RPMs have faster access times because there's less seek time to get the information from the particular sector and track on the drive. Now, this is tied into another term called latency. After a track has been reached by the read-write head, latency is the delay in time before a particular sector on that platter can be read. So that's how long it takes for the platter to spin around for the read-write head to actually get that data. And it's directly related to that rotational speed. It's usually half the time it takes for the disk to rotate once. So for a very common 7200 RPM drive, the average latency will be 4.2 milliseconds. But for a faster drive that runs at 10,000 RPMs, it'll be a lower latency, say around 3 milliseconds. So those are some of the hard disk specifications you should know: capacity, cache, data transfer rate, rotational speed, and latency. And if you get a chance, get yourself a magnetic hard disk and take a look at it and look at all the ports, look at the information on the label, and see how it works. Connect it into your computer, see how the actual drive functions. So that's about it for this sub lesson.